start talking about YouTube. So, yeah.
Nikki here today?
Not at the moment. So, okay, not today. But she'll have office hours at 2.
Okay, that was
Yep.
gonna be my.
Yes, office hours. Hello, folks. We're just starting the recording in the midstream of conversation as usual. What day is it? It's Thursday. It's not garbage day. That means I don't have office hours, but Nikki does at 2 o'clock. Cass has office hours tomorrow morning. I'll have office hours Monday afternoon. Cass has them in the morning, and then we're back to Tuesday with Nikki, and then Wednesday I have them. So every work day between, you can talk to somebody about homework.
Does Nikki also do R?
Yes. Yes, both TAs should be able to help you in both programs. That was part of their assignment, is to make sure they can figure it out. And I know Nikki's proficient in both in particular, so you should be good with that. And if you want to do your homework in SPSS or some other package, you could actually do that too. I was going to point that out since that is still a thing for a lot of people to use. I'm not going to hate on SPSS. Inside lecture 2 and 3, and also inside lecture 4 that I'm still working on, I have these pages periodically where I have syntax in 4 different programs to do the model. The bottom here is SPSS syntax. So this can be a template that you could use if you wanted to use that package too. But I know for sure it will work in SAS, Data, and R because I checked all of the answers myself. So, all right. So what we have today then is nothing new. I gave up on trying to start a new topic. I'm still working on the slides. This class is 4 years old. So whenever you open something you did 4 years ago, you're like, oh, I don't like this anymore. I have to fix it all. So it's taking longer than I thought, but that's just as well because this stuff is complicated. So it's, I think, a good thing to slow down and make sure that we have the primary concepts before diving into further details. So next week, my intention is to start Unit 4, which is random slopes of level 1 predictors, as well as cross-level interactions that explain them, and a little bit about estimation, which we have sort of waved our hands at up to this point. We'll see how much we have time for in class. I may opt to record videos outside of class for certain topics that so that we don't get too far behind relative to what I had planned. But what you should be working on now is homework 2, due next Wednesday. It should not be that bad, as usual. If you get stuck on something for more than 15 minutes, what do? Stop. Send me a screenshot. Put it away and move to something else. Don't kill yourselves. That's not the objective. And if you do figure it out later on, let me know so that I don't end up needing to email you something you've already figured out. All right, so where we are then, I wanted to go back through the models in example 3 that we had already been through. And then we have the exciting conclusion of what do you do with a negative contextual effect, or a contextual effect in the opposite direction. Do you remember that? That was our cliffhanger for Tuesday. Yeah, you can tell I'm out of television to watch if I'm inventing cliffhangers out of model results for semi-fake data, as I believe this data set to be. But so what we talked about last time then is we went through the process of adding predictors into the model to see what happened in terms of the variances for the outcome that they explain. So I'm trying to give a specific example of more general principles. So I purposefully built the model for each of the 2 predictors in this example in different ways so that we could see the combinations in terms of what happens. So model 2A, which we looked at last time, we are predicting math in like 7,000 students within, I think, 190 schools, something like that. And we are doing it in this model from just SES, socioeconomic status of the students. And because I can't say SES reliably, can we just call that money? You're good with that still? Okay.
Lisa, did you mean to share your screen?
I do. Thank you, Charlotte.
Sorry.
I hadn't gotten far, though. I had only pulled up the handout and started waving my hands at it. But thank you for the prompt. Okay, are we good to go now?
Yep, all good.
Excellent. Thank you. I appreciate that. Okay, yeah, hadn't even moved it yet. Just waving the pink mouse around. And yes, I know it's a little annoying, but I got tired of losing my mouse across the various screens, so I made it giant and pink, thinking I would always find it that way. So, socioeconomic status, otherwise known as money, in this model has been cluster means centered. So synonym for that as a more general name is variable centered, because the idea is that you are subtracting a variable, not a constant, and subtracting a variable fundamentally changes the information that is left in the predictor. I'm going to try to use the word information or info as sort of a shorthand for predictor variance because I felt like folks are getting confused when we talk about the variance that's in the predictor versus the variance being explained in an outcome. So I'm going to go info for variance on the x side and stick with variance as the term on the y side. So the information that is left over in this variable after subtracting the cluster mean is purely within cluster information. Do you have more money than the other kids in your school? That's what's in here. So it's relative socioeconomic status as the variable. So that means this variable contains only level 1 information, only 2, or a mixture of both.
Only level 1.
Only level 1. Therefore, which variance term for the outcome is it going to potentially account for? Yeah, the answer is always the one in its row as a general principle. But yes, level 1 residual in this case. So we add it to the model. It has a significantly positive slope. So for every unit more money you have than your school, your math, your student math goes up by 2.19. And lo and behold, that did explain 5% of the level 1 residual variance. And that reduction in residual variance made the random intercept variance go up a tiny bit. Okay, then we added the cluster mean for money, centered at 0 because 0 was already the mean of this fictitious variable. So does this variable, cluster mean SES, have level 1 info, level 2 info, or both? We got 1 vote for 2? Anyone else want to vote? 2 votes for 2. 3 votes for 2. 4. Zoomers are voting. Everyone, yes, 2. It only has a C. That's how you can tell in terms of the notation. And it's going as a predictor in the level 2 model. So this is only level 2 between cluster variance in this predictor. Therefore, what's it going to explain? 2's again. 2's have it. Yep, this guy right here. The random intercept, the one in its row. Yes. So when we set up our model this way, we have divided up our predictor variable into its level-specific parts. So each stays in its lane. Here's the level 1 within school effect of SES. For every unit more money I have than my peers, my math goes up by 2.19. For every unit more money my school has than other schools on average, the school's math goes up by 5.86. And if I want to know the contextual version of this, that's between 5.8 minus within. 2.2 gets me the contextual slope of 3.6 down here that I asked for as a linear combination of the 2 fixed slopes. And lo and behold, it accounted for another, let's see, it's about 68% of the variability. Change, it came out of the negative, is a little bit higher, but this is the number that I would report. So 68% of the reasons why some schools have better math outcomes is because of school level money. 5% of the reasons why some kids have better math scores than other kids is because of kid level money. That's the story so far. Okay, questions? Okay, now why do I like doing it this way? I've made that abundantly clear that I have a strong preference for this. What do you think?
Because you know exactly what the within is measuring, exactly what the between cluster is also measuring, and then you can, from there, you can get the contextual pretty easily, but you don't have to do any sort of guesstimation of what the within what's measuring for the constant there.
Say the last sentence again.
I don't know if that's right. Because with the constant mean centering, is it the within predictor that you're not certain if it has level 1 and level 2 predictors?
So yes, with the alternative, which is what I'll show you next, you're not sure what you're going to get because it depends on what else is in the model. So the reason I like this is that if I don't have this slope in the model, what am I assuming about it? 0. So I'm assuming there's no impact on student math of having more money than the rest of your school. That's what I'm assuming. If I leave this one out, what am I assuming that it is? 0. There's no impact of going to a school with more money on your school's math. You know what you get, because variables have been carved up into their level 1 within specific information, level 2 between specific information. And if you want the contextual effect for their difference, which tells you how different those two slopes are, you can just ask for it. So the alternative then, which goes by a number of names as well, grand mean centering is the most common term, but I don't like that term because the concepts apply even if you choose a different constant than the grand mean. So centering with a constant or constant centering is my preferred term, but I'm trying to link to the broader literature here. So in this case, this is what would happen if we didn't use cluster mean centering, and instead we just put in the level 1 predictor centered such that 0 is the reference, because that was near the mean of the variable. So then, does this predictor, not cluster mean centered, but just constant centered, does it include level 1 info, level 2 info, or both? Okay. 2 hands, maybe? Like, both. Yeah. This means all done, I think, in sign language. That's like one of like 2 things I know in sign language. More, all done, please, thank you. Yeah, I only know the sign language that my son knew at age 6 months. That's it. So after he started talking, we didn't do that anymore. But it was really cute to watch him go, you know, please, peach, peach. But anywho, peas. Level 1 and level 2. That's the correct answer. So when we only put in one slope, do we get the level 1 effect, the level 2 effect, or both? Level 2 is the vote?
For that one, yeah.
It goes with this guy. Yeah, if this guy has both in it, what's its slope going to have? Both. It's the smushed effect. So smushed effect means it is a slope that is being estimated assuming, without testing, that the within effect is the same as the between effect. So if we compare this solution, where we have one slope trying to do the job of 2, against the right answer here, in that the right answer meaning we've separated the effects across levels, the within slope is supposed to be 2.19. That's a level 1 slope, but this version of the level 1 slope is 2.39. It's too high, it's biased upwards, and that's not a coincidence because it's partially biased by this 5, which is bigger. So it's being pulled to look closer to the between than it should. Not pulled by much, obviously, but just pulled a little bit. And you can tell that this is the smush slope if you were reading about this in a paper, if that variable was not mentioned in the results section or their tables at level 2. And they didn't mention any kind of cluster mean centering or latent centering that would have otherwise addressed it. You can also tell by looking at pseudo R-square. So we get pretty close to the same 5% reduction in student math variance. It's a little bit off because of it's not quite the right effect yet, but this one's the dead giveaway. 44% of the reasons schools differ from each other in math is being predicted by student SES. That is logically inconsistent. The only way that a student variable could predict school anything is the school info that's buried within it. Like a Trojan horse. Do you know that expression? I don't think I can explain it very well. You'll have to ask the Google about it later. But it's like I want to go with Rome, maybe? Roman Empire or something? Greek. Okay, see, can someone explain it better than me, please? What's a Trojan horse?
You put the people inside the horse, they're going to kill you. You give the horse to your enemy, they jump out like a birthday cake and die.
Yes, so you put the soldiers in the horse, and then you put the horse somewhere, and then they jump out and say, hey, surprise, you're dead. Yeah, so like the level 2 variance is like sneaking in there, like a Trojan horse.
But
So.
if you're Monty Python, it's a rabbit.
Okay. I do not do Monty Python, I'm sorry. I'm one of the few people who doesn't think that's funny. I never got it, but I know I'm in the minority on that, and I'm also one of the few people who doesn't like Taylor Swift, okay? I know, fight me.
I'm a Trojan horse.
Yes, I didn't have an opinion on Trojan horses before this, but I just pulled that one out of nowhere. Now you can see that I know nothing about history or culture or geography or basically anything but this. Everything else had to like go by the wayside. So,
Do you have a particular issue with Taylor Swift, or you're just not a fan?
I don't think she sings well. I know, they're like, she did not just say that. Now, that's not necessarily a deal breaker. There are a lot of artists that are very entertaining and excellent musicians who don't sing well. At the risk of like pissing off the entire world, I'm not going to start naming who they are, but you know, that's a whole thing. Like Bruce Springsteen is a good example, right? Not a fantastic vocalist, but he's a great entertainer, puts on a great concert, memorable songs. I think she's sort of in the same category. I don't listen to it. That's all. So, I don't know. All right. No, I know, I'm just sharing. We're riffing today. Ding ding. The Zoomers are like, wait, I need to defend her honor. What? I am putting us on YouTube, and my 5 people who are going to watch this video are going to be horrified. I know, I'm going to lose all my hard-won subscribers.
Down with garbage to the lady.
Yeah, I have to think I'm not that much of a target, right? No one really gives a shit what I think about Taylor Swift. And she's going to go on making millions and selling out the world in concerts, and she has a movie about her concert. Like, there's nothing I could do to Taylor Swift. She's having a good day. You know what I'm saying? All right, so Trojan horse, let's bring it back here, like 6 digressions previous. Level 2 variability cannot be accounted for by a level 1 predictor. The only way that happens is through the Trojan horse level 2 variability inside the predictor that is doing the work. And we saw from the previous model that what we should have had for an effect size at level 2 is 69% of the variance, and we only have 44. That's because the model is misspecified more so at level 2. The reason that we only got 44%, whereas we should have had 69%, is because this model is saying the between slope is also 2.39. The between slope is 5.8, so it's off. And if you get within and between slopes that are in different directions, that can actually make your intercept variance increase rather than decrease. So misspecification shows up in a variety of ways. So we fix it by adding this one, which I think is where you were going. The cluster mean for money is entered into the model to control for the level 2 variability. So this model is fine, but it's a different version of what you get. So under constant centering for the level 1 predictor, student level money still has level 1 and level 2 info in it. But what we've done is control statistically for the level 2 info through a separate predictor. So now the unique effect of constant centered level 1 student money is just the part of its variance that it has uniquely, that's within. So it matches what you get out of the other model, even though the slope is multiplying a different variable.
So is this like, I'm thinking about literature I've read,
Okay?
and the Smush gets published a lot.
Yeah, it does.
So are like none of these people methods people, or is this like a newer discovery, or do reviewers just long hair don't care or don't know?
Long hair don't care? Is that what you said?
Yeah.
Okay.
This boxing, can I go back? Long hair don't care.
Okay. I know dirty hair don't care, but that's maybe a different problem. So the question was like, why is there so much smushing in the literature? Do people not know any better? I think that's mostly true. This is not new. Like this dates back to, the first Raddenbuch and Bragg textbook was what, 89, 90, something like that? Like this is not new information, and it's been written about 87,000 times. Like everyone and their dog has written a tutorial about this, including myself, which are some of my most highly cited papers are on this topic. So yeah, I'm going to milk that cow too. But I think that where it gets confusing is when some people say, well, if you're theoretically interested in the smushed effect, that makes it okay. Yeah, and then that's the face I give them. No. I don't know why theoretically you'd want the wrong model. That doesn't make any kind of sense to me. But as long as there's room for sort of preference, and you can say, well, I followed this person and this person has this preference, and they did it this way, and that's why I'm doing it that way, I think that is an argument that can sound convincing, but methodologists should know better. Like, it's not okay. And this is the simplest case, believe it or not, where we're just talking about fixed effects as main effects without random slopes, without interactions. The same problem happens, and it's much more complicated to spot and to fix in those environments, and that's what I'm still working on in Lecture 4, to try and explain that in the least painful way as possible. Question?
So in this model, in the unsmushed model, you use the cluster mean?
I still use the cluster mean. The level 2 predictor is the same. It's the same variable.
No, I might have just like misunderstood.
Okay.
So for the grand mean centering,
Yes.
so we don't need to compute a different level 2 predictor beyond just, okay, so we don't actually have to use like the grand mean of the entire sample?
No, what you subtract for your constant is up to you. That is completely irrelevant to the kind of information the predictor has. So it is literally the same variable where 0 was the already meaningful is the average or near the average, and so I just left it alone. It's the same variable in both models, but it's acquiring a different effect because of what it's paired with. In the previous model, it was paired with the level 1 only variable, so cluster mean money had to do all the work to get the right level 2 effect. Here, cluster mean money is filling in the gap of what the level 1 slope could do by itself wasn't enough. So it's literally filling in the gap of getting from the 2.2 up to the 5.8. The gap is 3.67. So this is the contextual effect. It is the extra effect of going to a school with more money than other schools on the school's math after controlling for how much money you have in an absolute sense, not a relative sense. Because this is level 2 and level 1 information in student SES, meaning it's the original full variable that you're controlling for. Another way to say it, this contextual effect is the difference of between minus within. It is also the effect if you picked up a child and moved them to a new school, this is how their score would be predicted to change, because they are keeping all their characteristics with them when they move. Yes?
Yeah. I have a question about the interpretation of these things, because we saw that in multiple linear regression, for example, we can interpret those effects saying, this is the effect of this predictor after controlling for the rest of the predictors.
Mm-hmm.
So let's assume that instead of the contextual effect, we have the between effect there.
Okay.
That we know is not controlling for the original values of the predictor at level 1.
Yes.
However, the interpretation from a multiple linear regression perspective would be that's the cluster effect after controlling for the values of the other variable, which is the predictor at level 1.
Mm-hmm.
But here we see that the interpretation is the same, but we are saying that the original values of the variable at level 1 were controlled for, and now we are looking at the effect at level 2, right?
I think so, if I
Okay,
follow
so
it.
what's the difference here?
Okay.
There.
So another way to explain it, these two variables are uncorrelated. So the unique effect is the same as just the effect because they're not competing for the same variance. There is no distinction. Each of these is a bivariate relationship with the outcome at that level, whereas these two variables are correlated. So then the unique effect is different than the effect of either one when it's by itself.
Okay, yeah, that makes sense.
Yeah, so it's easier, I think, to understand how you get to this place, because what does this variable have uniquely above the cluster mean? It has the level 1 info. So the unique slope is based on the level 1 info, that becomes the within slope. This one, though, this is level 2, but there's also still level 2 in here. So it's like the extra level 2 that it didn't have, which is weird to think about, but remember, this is only for one person. You can't make a very good extrapolation in most cases as to what the cluster is like from one person's data. So this is filling in the rest of the people to help with that extrapolation to characterize the cluster accurately. So that's why these are both coefficients that depend on having the other in the model. Without cluster mean to control, this is smushed because it has to do both. Without this one, this steps up to be between because there's nothing that it's competing with. Better?
Yeah.
Okay,
Thank you.
sure. So relative to the previous model in terms of variance explained, this is where we were at. Level 1 was pretty close to accurate, a little bit off. Level 2 was insufficient. Which of these two is going to change from adding in cluster mean money? Level 2 or level 1? Level 2, this one. Lo and behold, here's the smushed model. Here's the change after adding in the cluster mean to control the level 1 predictor for its level 2 part. And lo and behold, we pick up 24% more variance. So I say specifically, this is the contextual effect size, because that's what you added to make that happen. The level 1 R-square went up a little bit too, because now it's the right one. It's based on the full within effect and what it wants to be without contamination of the between, whereas in the smushed model, it was close to that, but not quite. And this on the bottom here is the same buildup that we did using cluster mean centering, so that you can see that the intermediate step looks different, but we end up at the same place in terms of the variance explained. It's an equivalent model. And if you went through the -2 log likelihoods, the variance component estimates, and all that stuff, it'd all be the same. So in this situation, when you only have fixed slopes and you've entered a level 2 and a level 1 predictor, you're good to go either way. And it's a choice which one you want to talk about.
Why is it called pseudo R-squared?
Because it can go up. Or the R-square can become negative, meaning the variances went up. So pseudo R-square is used for any kind of model in which there's not really a true unique R-square and you're trying to come up with something that passes for one. This is also just a side note. The way that I'm computing it is not optimal because it does occasionally result in negative pseudo R-squares for predictors that do not contribute. The alternative way of computing it uses a model implied total variance rather than a model without the predictors. And that's in the Wrights and Sturba R package to compute these things. So there are some conditions in which you can use that R package in which you can't, and I didn't want to get into the weeds on that, so I'm computing it sort of the straightforward way because you can always do that regardless of what package you're using. But it is important as part of your analytic methods section where you're describing what kind of models you used and what kind of software you used to provide this type of detail. This is how I calculated pseudo R-square, so that your readers can at least follow what you're doing and decide whether they want to agree or not. Okay, how are we doing?
Lisa, I had a quick question.
Yeah.
I'm guessing the answer is no, but can you estimate the correlation between level 2, like the U of level 2, the random variance, with the residual variance?
So can U be correlated with E?
Yes.
No, that would break the world.
Yeah, that's what I thought. Okay.
Yeah, that can't happen. Like that's like a definitional thing, that the levels are supposed to be uncorrelated.
Is that like the IID part of the independent and individually distributed error?
No, I would not say that, but this is, in order for these models to work the way they're supposed to, the levels are uncorrelated.
Okay.
So U and E are not related, ever.
Okay.
Yep.
Thank you, Lisa.
No problem. Okay, so where we ended up then, we added a binary predictor. Not a great example, but I just needed to have a binary predictor so I could demonstrate that the same concepts apply if you have categorical data. So this is whether or not a student identifies as non-white, where white is the reference and non-white is the one group. We add them into the level 1 equation, all by itself with nothing for it at level 2. So what am I going to get back? Yeah, smushed effect. Even though it's binary, that doesn't matter. So this non-white slope is significantly negative. A student who identifies as non-white is predicted to have their math score be lower by 2.7 Assuming what? Cough, cough, homework question.
Assuming that there's no additional contextual level to effect.
Yeah, no contextual effect, because contextual, another way to say that is the difference of between and within. If there's no difference, then having one slope to do the work of two variables is okay, in theory. I still don't like it, but it's more defendable that way. So assuming no contextual effect, this is the coefficient that distinguishes different statuses of our students. And we have evidence that it is a smushed effect via the change in R-square. So it picks up 2% of the level 1 residual, which is what it should have done, but it also picks up some of the random intercept. Not much, because it's not a strong effect, but it's there. So we fix it in the same way that we fixed the student money variable by adding school mean money. We're going to add school mean non-white. So that sounds kind of weird, but think of it as composition. What this variable represents is the school composition, the proportion of students who are non-white at that school. And in the descriptive statistics at the beginning of this handout, the mean for this variable was about 0.27. So I rounded it up to 0.3, and that's going to be my reference. So the reference school at this point has average SES with respect to this variable, and it has 30% children who identify as non-white. And I have a note over here. I didn't have to do this because 0 is meaningful, but I wanted to be able to talk about the level 1 slope, and you can't do that at a school that only has one type of child, which is what a 0 proportion would imply. And then where we left off was this. So we have a negative significant coefficient for the within school effect. So two kids who go to the same school, a child who identifies as non-white is predicted to have lower math by 2.89 or 2.90. Now, this is my contextual effect. It's in the opposite direction. That can happen. So if I go strictly speaking, a positive slope would mean what? Yeah, I'll take gestures on this one. Wait, this way. Nope. There we go.
Would that be for every 1.3 units
Other way.
or,
1 unit next. Always.
oh, okay. So the hold on, money. Right,
This isn't money. These two are money. These are the binary variables. So non-white is a binary predictor, and this is the school proportion of children who are non-white centered at 0.3. So this is like the cluster mean.
yeah. So for every 1.3, for every unit of that, you have your 1.3 better.
Yes, better.
Or I don't mean that.
Well, more math is better. I think
Okay,
that's
all right.
usually what people would accept. So yeah, for every unit increase in this variable, school math or kid math? School math goes up by 1.35 after controlling for whether each individual child identifies as non-white.
What is the unit of non-white though? Like,
Great question. What is a unit in a proportion? Proportion. Yeah,
I moved my decimal over.
yeah, sorry. So, but this variable is between 0 and 1. If it were a percentage, it'd be 0 to 100. And so as the mean of a binary variable, its natural scale is proportion. So a change from 0 to 1 is the entire possible range of this variable. A 1 unit change is all of it. That's going from a school with no non-white children to a school with all non-white children. So this coefficient is sort of like off scale, relatively speaking. Like that's the most change you could possibly have. So it's a little bit weird, but it is opposite in direction. Now, does this mean that there is a positive between school effect of school composition non-white?
Which number?
Well, this number right here is a positive number, and that's my contextual slope, right? This is the effect of going to a school with more non-white children after controlling for whether or not a given student is non-white. This is a positive contextual slope. Does that mean that the between school effect is positive? No. How'd you get there? He's like, I scrolled down. Another way to think about this is the difference. So I could say that the between slope is less negative by 1.3, I think. Is that right?
Okay.
Yeah. So this is the between slope down here. It's minus 1.5. So schools that have more students who are non-white have lower math outcomes. But after controlling for whether an individual student is non-white, the direction of the coefficient switches. And yes, this is confusing. And rather than wave my hands at it, I decided to make some pictures. Okay, did you have a question? Or, no, just waving. Okay, all done. Yeah. Not quite. It's only 111. Yes.
And when we run those contest 1Ds, the zeros and ones
Mm-hmm.
correspond with the order in which things are put in the model.
Order in which it puts it in the model for you, not necessarily the order in which you wrote it.
Okay.
It holds for main effects, but for interaction terms, it makes all the main effects come first and then the interaction terms. So if you order it differently, it doesn't listen to you. I did learn a trick to solve that problem, but now I can't remember what it was.
No, I just
So.
remember I had an issue.
I'm sure. So it's this is what you consult. That's your order.
Okay.
Stare at your output. Question?
Yes, so now that you mentioned that that's not the between effect, but can we interpret that 1.35 as the expected increase in school mean outcome for every 10%, for example, a student's composition, blah, blah, blah?
Yes.
Can we say that the expected school mean will increase by every 10% more of a student with that characteristic?
Yes.
Okay.
And if you're like, I want to make sure that I have this right, or you want to make a table where that's done for you, I did that actually. I did it in the last model. But yes, that'd be an alternative way because this 1.35 is the difference between 0 and 1, which is all the range of the variable. Per 10% more might be a more useful way to talk about it. You just move the decimal over. So 0.135. And then the standard errors decimal would move over too.
So in that case, we would be saying that a school mean is predicted to increase by 10% more of the students after adjusting for the original values of the predictor of level 1.
After
that's-
adjusting.
Yes, but that's not the same. In the other case, if that would be the between effect, we would say that between schools or among schools, that would be the expected change based on school composition?
Without controlling for individual status, yes.
Okay, great.
Yeah, so the between effect is negative. The within effect is negative. It's just that the between effect is less negative, and that's why this is a positive number. And this is the point where your readers are going to be like, what? And they'll ask you for a picture.
I mean, to be fair,
Yeah.
Yeah. I'm still a reader in this situation.
Yeah, no, I think it's really important to try to put yourself in your reader's shoes and, like, are they going to follow you? And do everything you can to make it so they can follow you, because it's tricky. It really is.
How did you know it was like 10% more non-white?
If you just change the scale of this variable by dividing by 10, then a unit is 10% rather than all the percent.
Okay, that makes
That's all. It's just it's easier than thinking.
I just couldn't find the answer.
Yeah, I did that in the last model. And so if you're like, okay, like this is breaking my brain to have these in opposite directions, I hear you. So I switched back to the cluster mean centered version that I prefer. And then it's going to break your brain in a different way. So I cluster mean centered non-white. So what are the possible values that children can have of this new variable.
-1 and 1.
It's only 1 unit difference.
Yeah.
So if a school was 50-50, minus
-0.5.
0.5 and positive 0.5. And if a school was 60-40, yeah, I'm like, which way does it go? -1 and plus the other is where I'm going. Can you have a score of 0 if you cluster mean center a level 1 predictor that is binary? No. So who is my intercept for? A person that doesn't exist? That's really dissatisfying to me. Really dissatisfying. So that's where I'm like, maybe I don't like cluster mean centering all the time. But the premise still holds. This is then still a 1 unit difference. It's just that your starting point is some negative number over to a positive number because they're mean centered for your cluster mean. And yes, here are the per 10% that I did. So in Stata, I did this explicitly by dividing the slopes by 10, both of them. And I did the same thing in R in a, yep, here we go. Dividing the slopes by 10 so that you can get those numbers as part of your output. That way, if you want to build a table or something and not have to move the decimals over yourself, you can. That one doesn't look right. I need to recheck this number. That does not look right. Something went awry there. Here is the cluster mean-centered solution then. Here's the previous constant mean-centered version. So this one and that one are the same. They both represent the within effect for SES because in the cluster mean-centered model, that's the only possible interpretation because it only has level 1 information. Here, it becomes the within effect after controlling for level 2. Same thing is true for the non-white level 1 effect. They're the same number, even though they're multiplying different versions of the variable. After controlling is what happens in here. And then the cluster mean variables are your between effects. So for every unit more money your school has, the school's math goes up by 5.3. For every unit more money your school has, math goes, or nope, for every unit more non-white, which means going from 0 to 1, the school's math goes down by 1.5. Contextual effect is positive, meaning that the between effect is less negative. All right, I'll check on that number and fix the handout later. All in told, our model explained 70% of the level 2 variance and 7% of the level 1 variance. Keep in mind, though, this 70% is out of what originally?
The 18% of random distribution.
Yeah, you got to go back all the way back to the empty model, like 12 pages ago. And it was only, what, 18%? So what I have is 70% of the 18% that was at level 2. When you put it that way, it's not as exciting. But that's what it is. And then what's 1 minus 0.18? 82? Nailed it. I have 7% of the 82% at level 1. And if you put those back together again, like if you do 0.70 times 0.18 plus 0.08 times 0.82, that gets you pretty close to the total R-square for the model. It's a reasonable approximation, which is 0.18 overall. All right. Want to see some pictures? Please.
So just to reiterate, the Lincom statements in Stata for the 4C, those are just the -1 in the Lincom for the getting the slope to be 13%.
Mm-hmm.
How did you decide 1 versus -1? Is that the contextual slope on that?
So the first one, I was asking for the between slope, which is what this model gives directly because this is the cluster mean centered version. And the contextual slope I had to make as between minus within. And so that's why this is the between slope that gets the 1, and this is the within slope that gets the -1. That's why. And they both get divided by 10. So. Is this, and now I'm checking my math in R. Yeah, that's why, I think. Oh, nope, no, it's right. It's good. I was judging the numbers. This one got moved over, and that's the 1.5. Okay, I'm with you. All right. I got it. So here's some words. And I have a disclaimer here that this is not a write-up that follows the handout. This is like putting it all together, how would I describe what happened, and skipping over things that were broken. So this is describing what happened with respect to the empty model, centering of predictors, and then describing the within effect, the between effect, and the contextual effect of each in one fell swoop. So I did that for the SES variables in this paragraph, added the non-white variables in this paragraph. And then I thought, we need some pictures. Aren't these pretty? With the purple and the green and the contextual. By the way, purple for person and green for group. I also heard from Kaylee. Thank you for that mnemonic. That works for you. Now, how did I make these things? And what does it mean to show it in different ways? So this plot here on the left is focusing on the money effects. I held constant students who are non-white at 0 and proportion non-white at 0.3. So this is for a white child who goes to a school with 30% non-white children, so that I can isolate the SES effects. And this picture on the left is a cluster mean centering kind of picture where the x-axis is money relative to your peers. So the middle is you're at your school's mean, whatever that is. Lower is you're lower by 1 standard deviation of the within variable, and higher is 1 standard deviation of the between variable. So consequently, the within slopes are given by the slopes of the purple lines here. So this is the effect of having more money than your peers. And the difference between the lines is showing the between slope. So for every unit more money your school has, your math goes up by yay much. And the particular values that I decided to plot were based on the standard deviations of the variable or close to it. So in Excel, this is the new version of the Excel sheet that I posted like a week ago. So if you download the zip folder again, this will be in here. And this is the tab called Plots. I decided to make it in Excel for transparency's sake. Yes, I know all the programs make prettier pictures than this, but come on, this is pretty. So I typed in all of the coefficients, okay? And I have a note that I included the contextual effects, but I'm not actually using them at this point. So I have the intercept, the within, between, and contextual SES effects, within, between, contextual non-white effects. Then the question is, how do I come up with values to plot? Well, depending on your predictor, it might be relatively easier to think of the within version of the variable or the original version. So for SES, it was easy for me to think about what low and high would be for the within version of the variable because I just looked at the descriptives for it. The standard deviation for within school money was about 0.66, where 0 means you're at your school's mean. So I just plotted low, medium, high as plus or minus 1 standard deviation on that within variable. Then for cluster mean SES, I looked at the standard deviation of that variable, and I went plus or minus 1. So I have a low, medium, a high person in a low school, low, medium, high person in an average school, low, medium, high person in a high school. And then I added them together to get to the original SES variable so that I could put that on my x-axis if I wanted to. Okay. Zooming in a little bit. So these values are just entered. This one is added together. Okay, with me so far? All right, now I have to give the rest of the coefficients something to do. So the other predictors in the model, if I'm not interested in showing their effects, I need to hold them constant at possible values. So this is the original non-white variable. It's easier for me to think about it in its original binary way. So I'm holding it constant at 0. Likewise, I'm holding the school mean constant at the 0.3 that I centered it at. So then I made the versions of the variables that actually went into this model as that column minus the centering constant, and the within column is the original minus the cluster mean. So they go into the prediction, which is computed here as a linear combination. So I know it's tiny, but you can see all the cells being highlighted. It's intercept plus slope times variable plus slope times variable plus slope times variable. Just make sure you get your columns all straightened up. And then I took the resulting scores and I transposed them so that it looked more like something Excel could handle directly. So then I have 3 different kinds of schools, 3 different kinds of people within a school, and using that within school SES as my x-axis created this picture right here. So schools that have more money have better math. That's the difference between the squares and the circles and the triangles. Within a line, students that have more money have better math, and that's the difference along the slopes here. Okay, how are we doing so far? Now, what's not in here? Contextual effect. Is that an oversight or an impossibility?
This one,
In the left-hand side.
possibility.
Yeah, I can't put it in there because of the x-axis. The contextual effect would hold SES constant at some number. There is no common number in here. So in order to show the contextual effect, I got to change my x-axis from within money relative to your mean to just money. Why is that doing that? There we go. So now I'm plotting this against original SES, where I still have low, medium, and high, but based on the school mean, I've eliminated the cells that would be more than 3. So I've got the 3 like lowest values for the low school, middle values for this school, and then highest values for that school. Now I can hold things constant. So the between effect is the slope of the lines through the means. That's the green line that I stuck in here. That's my 5. The contextual effect is the distance vertically holding original SES constant. Now I stuck it here. Could I put it here? Sure. Could I put it here? Sure. I just ran out of spots. So this is the only spot that I've got lines from all 3 people so that I can actually hold it constant. But these lines are parallel. There's no interactions. So the contextual effect is just holding constant, not necessarily constant at any particular value. But the key idea is that you have to show the original variable in order to show both the contextual effect and the between effect in the same plot if you wanted to. Okay. How are we doing?
So just so I'm understanding, is to show a contextual effect, you need to go from within to between.
And to show a contextual effect, it would be an x-axis that you can hold constant at an original value, not just relatively low or high.
Yes. I might have misheard you when you talked about going from, like, you needed to go outside of within.
Yes, so the difference is it's like this is the same data being plotted.
Right.
It is the same 9 numbers, right? It's just what it's showing. So on the left here, the x-axis is relative money only, where average means you're at your school's mean. So that's the middle triangle, the middle circle, and the middle square are all aligned on the left-hand side. Whereas they're offset here. And in order to have the middle value be the mean and then to show relatively low and relatively high, I don't have the same, like I don't have 5 possible values for every line. I sort of cut it off purposefully so that I could still convey the idea of more than usual as moving off of the mean within any of these lines. So the between effect is not holding things constant. It's at the mean for each variable. or each line here, and the context effect is holding X constant, holding your student constant at, you make 0 money, which is a good thing here, it's an average. So it's up to you what you show and what you want to emphasize. If you like contextual effects, you don't even need to do this. Watch. I don't like the green line. Okay, there you go. Take it out. If you're like, context effects are weird, I don't like them. Okay, do it this way. Up to you. Now the other one is trickier. Now I am switching what is being predicted for the plot versus what is being held constant. And I held SES constant at 0. So we have an average school and an average student within that school, and I'm going to vary white and non-white. This is a typo on that. I can never find my own typos when I'm staring at them, of course. Now the tricky part. For students, how many possible values of non-white are there? Like, there's really only 2, right? This is a binary variable. So like in my head, I started with this column. I knew I needed something in the middle, so I initially left it blank, but it's like, well, I have a 0 and I have a 1, and I have a 0 and I have a 1, and a 0 and a 1. And then I wanted to have different kinds of schools. So the standard deviation of this variable was 0.3, and my centering point was 0.3, so that would be average. But if I went all the way down to 0, then I'd be in weirdness. If I showed a prediction for a school with no non-white kids, and I showed what the non-white effect is in the school that doesn't have the non-white kids, it's weird. So I made it 5%, just to avoid the weirdness. So my low, medium, and high, with respect to composition, that's what this variable is, 5% non-white, 30% non-white, 55% non-white. So based roughly on a standard deviation, plus or minus, but not quite. Then I had to do the math of like, okay, so what would a student get if they were at their school's average? And I stuck 0.5 in here to go with this. I stuck 0.3 in here to go with this, and 0.55 to go with that. Then I made it do the math, so I created my centered level 2 predictor by subtracting the centering constant that was in my model. And I created the within level version of it with the original non-white minus the original cluster mean. And then I get these values. And again, linear combination, same formula as above. Non-shite. That sounds like some sort of like Middle English or something. It heard me talking about the Trojan horse, I guess. It's like non-shite. That sounds like a Monty Python word. Why won't you grow? All right, I'll have to fix that later. It looked fine on my other computer. So this one is between and within effects of non-white, where it's within, same as up above here. Does anyone understand what the hell this x-axis is? Anyone? I don't. Like, this breaks my brain. The ends are the logical possibilities of a white student and a non-white student. The middle is when you're at your cluster mean. And so the plot is showing the gap that results from the difference in the binary predictor, but the x-axis is weird. So this is going to break your reader's brains. I would not do this. This one I did to try and show all 3 in parallel up above, where the green line is through the means of the people that don't exist, and the contextual effect is holding it constant. So now the x-axis is back to something that I can interpret. It's 0 and 1. And I added outside so that I could keep the picture in the middle. So these are white students, these are non-white students. And then the difference between the lines, holding non-white constant, is the contextual effect. And you'll note that the lines are in opposite order The squares are on top, the circles are in the middle, and the triangles are on the bottom because the context effect is positive. So the greater the proportion of non-white students, the higher the math. And this little green line is going to break your reader's brains. So I would not do it. This is what I would do. Simplify. So there's no easy way to show the between effect if you're going to plot the original variable on the x-axis and the original variable is binary. It's just weird. So that picture is difficult to explain. So I wanted to give you some ideas as to how you would talk about this in practice and plot things in practice, but it should always be guided by your data and what makes sense in the context of what you're doing. And I'm told ChatGPT does a good job of writing Canterbury Tales stories. Oh, that's nice. I don't think I want to read ChatGPT stories. It's probably listening too, but I'll start getting adverts for story writing on my Facebook page or something. All right. How we doing, folks? Ooh. Breaking brains? Breaking brains, taking names? Other questions or comments? Yes.
Not really totally on topic. Is that okay?
Sure. I'll tell you if it's too far afield.
Okay. Just conceptually, out of curiosity, if you cluster mean-centered one variable, do you have to do it to all your variables, or could you grand mean-center one and cluster? I don't know why you would, but I was just wondering conceptually.
So the question was, do you have to keep all of your model internally consistent? Like if you're going to do cluster mean centering, should you do it for everything? Or can you sort of mix and match? I would keep them consistent. Because you could. There's like legally there's nothing wrong with it, but you would be in the position of some level 2 effects in your model being contextual and some of them being between. And it's difficult to make that distinction in a way that I think is going to be easy to follow.
Okay, so it'd be a hotness express.
It could be. Where you can sort of hedge your bets is if you build a table that is not just what's in your model, but what is implied by your model. So like you could describe how you set up your model, but then have 3 rows for every predictor within between contextual. Because you know that either model can give you the one that it's missing. And then you can talk about whichever one you'd like to for each variable, and maybe it's between for one and contextual for another, but then at least the reader has all the information to sort of follow your logic. All right, other thoughts, questions? Okay, I have like just a couple slides we haven't talked about in here that I want to hit real quick, and then we'll call it good. So latent centering is the other option for doing this, where you let the model figure it out. You don't make up your variables ahead of time. You treat X just like Y in a multivariate model. So you would estimate a random intercept for X rather than build a cluster mean as an observed variable. Likewise, you would have a residual variable that has its variance estimated by the model rather than build a within cluster deviation. So graphically, it would look like this. The idea is that we're splitting up both X and Y into its pieces, and then we would estimate the between relationship directly among the corresponding intercepts and the within relationship directly among the corresponding residuals. This takes different software in a whole sort of different system, but for those of you who've lived in that world already to some extent, here's some M+ code and output that does that. I'm going to put off going into this world until we get to mediation stuff, because that's the point at where you would probably need to head this way as opposed to just could head this way. The other thing that we didn't talk about, level 1 interactions. I was going to put that in my example, but then I started looking more about it and realized that it was somewhat tricky. There's an order of operations problem in how you build your interaction term at level 1, and you get different things, it turns out. Yeah. So it's, do you center first and then make the product second? Or do you make the product first and then center it? Those are not the same. So there's a paper about it that I added to your reading list, and the product first and then center. This one, according to this paper, did the best job, but it suffers from the same weirdness in terms of what 0 means. There's no place at which everything is 0 like it's supposed to be. Centering first and then taking the product, which is what I would typically do, turns out that the product of two level 1 within variables can still have level 2 variance in it. So it's not really within. So I'm not going to have any examples of this because I'm not entirely sure, honestly, what I prefer yet. This is, I think, an open question in terms of future lines of research. We talked about this in terms of constant centering versus cluster mean centering, but we have not said one thing. So sociology folks in particular, people who have data that are collected for you from agencies and countries and stuff, like cluster mean money, probably is not the best way to measure that construct, right? Likewise, proportion of students who are non-white in this sample as opposed to like in this school overall that you would have from like a district level source. Like if you have better level 2 data than aggregating across the people in your sample, you should use that instead. So if you're in that situation, I would not do cluster mean centering because the cluster mean itself is not very reliable. Instead, I would stick with constant centering and then use the level 2 version of the information that comes from some other place. Then at least you're representing the same concept at both levels, not necessarily through the exact same measured variable. And do I have to do multi-level modeling? Yes, damn it. Yes, with a star here. Okay, I'm putting a poem in the chat box here. All right, I'll take a look at that later.
And that's after class.
Yeah, that's definitely beside the point here. So there are two other ways that people deal with clustered data. One is to use fixed effects. So if you don't have that many clusters or you care about each specific cluster and what happens to it, then treating cluster ID as a categorical predictor is sufficient to prevent smushed effects because you've saturated all the level 2 variance in your outcome. All you have left is within. So you don't have to worry about this if you use fixed effects instead of a random intercept for your clusters. Another option is cluster corrected standard errors. If you do that, you do need to worry about smushed effects. What that does is essentially take the E residuals out of your single level model, figure out sort of post hoc how, if they have a commonality, and sort of extract the intercept out of that residual sort of after the fact and correct for it with your standard errors. But you have not removed the level 2 information from your outcome, which means that you can still have smushed effects. So if you want to handle dependency in terms of the model for the variance that way, go ahead, but you still have to specify that your level 1 predictors in such a way that you don't have smushed effects. So that's one thing I think people really don't understand. This approach is not a panacea for everything. And I've also had debates with folks that say, like, well, that's not my question. Like, I don't really care about the schools, or I don't care about the countries. I just care about the people. It's like, but wouldn't you care that your model about the people is right? Like, even if you don't care about that, you still have to care. You know what I mean? So there's no get out of jail free card that I can grant you unequivocally. That's my opinion. But there's an extended article on your reading list about it that you can look at as well. So there, I think we hit everything now. Ta-da! I done class. Questions before we call it a week? That was my Huey imitation when he was like 1.5. I done eat. Anyone know what that means? That means, excuse me, Mom, I believe I am finished with dinner now. I would like to be excused. And toddler, I done eat. So, yeah, it happens.
Old Catholic school in Goodman still.
Yeah, no, nope. Sometimes I miss my inner toddler. Like, they want to talk sometimes, so sometimes it just feels good to yell and throw things. Like, especially when you're looking at this stuff.
Yeah.
Yeah, I know, right? Well, hopefully none of you yell and throw things as you're working through homework too. If you get to that point, put it down and then send me an email once you've recovered, and I'll be happy to help you.
You can also go to the splatter room and see the rapids.
Ooh, throw paint. Okay.
That's quite fun.
Yeah, I like that. Field trip. All right. Thanks, folks. have good weekends. Let me know if you need anything. Bye, Zoomers. To
I'm curious, like, always happy to help, yes, but